So in this lesson, we will be working on solving trig equations. It's going to feel sort of simple and then sort of complicated all at the same time. But like I just said, you can always check your answer keys or check your answers on your formula chart because a lot of these things will be there. So in the first set of examples, they're going to be more straightforward than the second set. But we're just going to be solving the trig equation specifically on the interval from 0 to 2 pi. Now the interval from 0 to 2 pi means that we are going from the typical x-axis around the circle just once. Meaning we're not going to have negative angles and we're not going to have an angle bigger than 2 pi. So we're only going to be working in one revolution of the unit circle for these sorts of things. So to solve these problems, what you're going to do is ask yourself to kind of think about the chart that we know in a backwards way. We know that the sine of pi over 6 is equal to 1/2. So like I know that x is pi over 6, but that is not the only place where sine of x is equal to 1/2. We also know that since sine is positive in quadrant 1 and quadrant 2, that there will be an angle here, pi over 6, and there will be an angle here that's pi over 6. Of course, when I'm talking about that, I'm talking about this being the reference angle of pi over 6, which means I need to know the actual angle from here to here to know what that angle measurement actually is. So it's not just going to be pi over 6, it's going to be an additional angle. And what is that angle in the second quadrant? 5 pi over 6. We know this because if 180 degrees is pi, giving it a denominator of 6, it's 6 pi over 6. 1 less than that would mean that this is actually 5 pi over 6. So we have two places on our unit circle where sine of x is equal to 1/2. It's at x equal to pi over 6 and 5 pi over 6. Now to check your work today, what you're going to do is look at your formula chart on the front, look all the way down sine. There will only be two places where we have positive 1/2 written down. What are those two angle measurements in radians? Look at your formula chart. All the way down sine, there's only two places where it says 1/2. One of them should be pi over 6. The other one should be 5 pi over 6. Do you agree? So when you're checking your work with this, because I do want to see this work working in the unit circle, but you can always check the formula chart to make sure you have the right answer. And we're going to be doing that the whole time today. That's kind of like a really basic problem. So we're just identifying what we know. We know that pi over 6, or sine of pi over 6 is 1/2, so then we kind of work backwards to figure out the other angle in a different quadrant. And then we have a problem like this. If we're solving for x, just a typical solving for x sort of situation, our goal is to get the thing with an x isolated first. Well, here's the term with an x in it, so we need to isolate that. Meaning I will subtract 1 from both sides and then divide by pi over 2. Wow, what? Divide by square root of 2. Now, at first glance, negative 1 over square root of 2 does not look like something I have memorized, but it's because I've always had you rationalize the denominator. What is negative 1 over square root 2 written with a denominator of 2?
Square root of 2 over
Yes, negative square root of 2 over 2. That's how we would really write it. Now, that should sound familiar to you.
Yes.
We typically know that cosine of what is square root of 2 over 2?
45.
Yeah, 45 degrees, so pi over 4. That is typically square root of 2 over 2. We know this. This is just some fun facts that we've had in our brain for a while. However, we need them to be negative. Which two quadrants is cosine negative in?
2 and 3.
2 and 3. So I'm going to have an angle here and an angle here. For both of these angles, the reference is pi over 4. So I actually need to figure out what this angle measurement is and what this angle measurement is. So for the green, remember, if this is pi over 4, the reference angle is pi over 4, and 180 degrees would be 4 pi over 4. What's that angle in the second quadrant? 3 pi over 4. And what's the angle in the third quadrant? 5 pi over 4. So my two angle measurements, where cosine of x would be equal to negative square root 2 over 2, is x equal to 3 pi over 4 and 5 pi over 4. And again, we just quickly check our work. Look on your formula chart for the entire column called cosine. There should be two places where it says negative square root 2 over 2. And those two places should be 3 pi over 4 and 5 pi over 4. Is that right? So here's about the two kinds of examples you're going to see in this section. One of them is very straightforward, where we're just trying to find x. There's no like solving to get it to say a normal trig function. And in problem B, we had to move some stuff around to get the cosine of x by itself first. Do we see the two differences in these problems? Let's do one more. Do we recognize this as something from the table?
Yes.
Restroom? Yeah, go ahead. In the table, what is typically listed when tangent of something is equal to square root of 2? Pi over 3. So 60 degrees or pi over 3. We're working in radians all day today, by the way. So that's what we typically know. But there's going to be two places where this is true because of the way we look at a unit circle. In which two quadrants is tangent going to be positive? 1 and 3. So here's my two angles I need to find out. In quadrant 1, that's a slam dunk. We know that that's pi over 3. We don't have to do anything with reference angles in quadrant 1 because the reference angle is the angle itself. But to find this angle, we know that this reference angle is pi over 3. I want to know what that entire angle is. So if we know that a full 180 is 3 pi over 3, that means that this one has to be, yep, 4 pi's over 3. So there are two places again where tangent of x is equal to pi, square root 3. It's at pi over 3 and 4 pi over 3. Okay. Comments, questions, concerns before we do some different types of examples?
Miss Quigley.
Yes.
I have like a little idea that I made it. I just wanted to tell me if it's true or not.
Okay.
You know how we found that right? When it's the first quadrant, that's pretty simple to solve. But when we get to the second quadrant, I just think it's one digit less than the 180 degrees angle. On the third quadrant, it's just going to be one more. And on the fourth quadrant, it's going to be one digit less from the 2 pi.
That is correct.
So I can just apply that to everything.
Yep.
Okay.
Yep. And if you have no idea what he just said, you're going to draw yourself pictures and you're going to write down all the stuff that I've been writing down. Okay. Let's keep going because we're going to have plenty of time to ask questions during the homework portion of today. Oh, yeah. When we finish notes. In problem D, it says the cosine of cosine of x equal to 0. Now, that is not on my chart per se, but isn't there a place where you can find zeros and ones along a unit circle? Yeah. If you look at the unit circle itself, there are two places where cosine would be equal to 0. 90 degrees, and where else? 270 degrees. Now, we are answering in fully radians today, so instead of 90 and 270, that would be pi over 2 and 3 pi over 2. Now, a question I'm expecting that somebody is thinking, why couldn't we just say negative pi over 2? Because we started doing that when we did inverse operations with this, like cosine inverse. I know that, but we have restricted ourselves to only solving these trig functions from 0 to 2 pi, meaning we're not going to negative 2 pi. We're just going from positive or 0 through the positive values to 2 pi. So don't answer any negative answers today. They're all positive. Yes? Okay. Now, how about sine of x equal to 0? Are there two places along the unit circle where sine would be equal to 0? 0 and 180, but we're answering in radians, which is 0 and pi. Now, if you're like, where are people looking for this? On your formula chart at the very top, there's the 3 different graphs. So once you notice that's up there at the top of your formula chart, you'll be good to use that. Last one in this section. Bless you. Sine of x equal to -1. There should only be one place where you see a -1 listed for sine. Where is it? Oh, but in radians. 3 pi over 2. That's the only place I know on my unit circle where sine would be equal to -1, since sine is the second coordinate, x comma y, along the unit circle. Okay. Comments, questions, concerns about these. These are what I'm going to consider level 1 questions. But then the next problems jump to like level 3 with no warning. So I want to make sure we understand this before we keep going. So we're going to pause the video for a second. So here's a good question. When do we stop and try to figure something out? When it says sine of x equal to a number, or cosine of x equal to a number, or tangent of x equal to a number, that's when you look at your chart for the one that's in quadrant 1. And once you know the angle in quadrant 1, if there is one, you will then find the other quadrant where it is also that value.
And then you write both of them down.
Correct.
Oh, okay, I get it.
Correct. So for most of these, there will be 2 answers. I mean, obviously, letter F we only answered once because there's only one place where sine is equal to -1. But most often, there's 2 answers for each of them. Can I keep going?
Yeah.
Fabulous. Okay, so those are level 1 problems. But occasionally, when we are solving when we are solving trig functions, it will dip into our ability to do quadratics, which means we're going to see squareds here. When we were solving quadratics back in like Algebra 2, there were like 18,000 ways to factor something. The ways that you're going to focus on are like the X puzzle or guess and check factoring and GCF factoring. We'll start with GCF since it's easier. In this first problem, again, the instructions say we're just working on that positive interval from 0 to 2 pi, so no negative answers. We want to solve sine squared of x plus sine of x equal to 0. It's set equal to 0, which means I can factor it. What do both of these terms have in common? Sine of x. So sine of x is my GCF. If I factor out the GCF, what are my leftovers? Sine of x plus 1. So it's like dividing out a sine of x from each of them, cancels one of the 2 in the first term, cancels both in the second, which is where the 1 comes from. And if you think back to when we just straight up factored like quadratics, when you got here, you used what's called the zero product property to say, okay, well, either the first term is set equal to 0 or the second term is set equal to 0. Because if either of those things are 0, the whole thing is 0. That's the zero product property. Well, now I have 2 equations like I did at the beginning in the level 1 questions. Where are the places where sine of x is equal to 0 along a unit circle?
0 or pi.
0 and pi. We already answered this. So 2 of my answers here are going to be 0 and pi. But then I have to work on the second factor in the same problem. I can't ask myself any question about sine of x yet because it's not isolated, so we subtract 1 from both sides. And now that it says sine of x equal to some number, now I look at either the chart or the unit circle to find some things I recognize. There's only one place where sine of x is equal to -1. And we've already answered this one as well. Well, where is it? 3 pi over 2. So this question has 3 answers. There are 3 places where this equation would be true. Yes?
Is there ever going to be restrictions where it says x can't do this?
Just pray we don't do
I
this.
can imagine that there are ways I could make an ugly problem where there are restrictions, like if you add in a logarithm or a square root or some sort of rational problem, but no. I won't ask you any, but not saying those don't exist, if that makes sense.
Start imagination.
That's all that matters right
Okay, did we follow that?
Yes.
So when it's got more complicated equations, especially when there's a square, we're going to have to utilize quadratic skills with trig at the same time. It's cool. Okay, so let's look at the next one. There are two terms in this problem, and one of them is squared. That's our indicator that there is going to be some sort of factoring and solving. What do both of those terms have in common? Cosine x. So that actually turns out to be my GCF again. When I take out my GCF, I'm left with what?
Cosine squared.
You missed something?
2
2 cosine of x
minus
minus square root 3
Oh,
equal to 0. Yeah, because that cosine cancels out. Remember, when you're taking out a GCF, it's like you're dividing out a GCF from each term. So these cosines cancel, and this square and this cosine cancels. And all of the leftovers go in parentheses. That's what GCFing things are. But once you have it in factored form, which this is, it's when you split it into two problems. Our two problems that we're going to work on are cosine of x equal to 0 and 2 cosine of x minus square root 3 equal to 0. The blue one should be easy. Technically, we've already answered this. Where are the two places along the unit circle where cosine of x is 0? Pi over 2 and 3 pi over 2. But the other one's going to require some work because it's not set equal to 0 right away. Acting like it's just a regular algebra problem, if we want to isolate first cosine of x before we get to the x part, what would I do? We want to get rid of this first.
adding 3 squared.
Adding square root of 3 to both sides. And then doing what?
Dividing by 2.
Dividing by 2. Okay, so we have cosine of x equals to square root 3 over 2. Does that look familiar to us?
Yes.
It does. Normally on your formula chart, what angle measurement is equal to square root 3 over 2? Oh, so cosine of pi over 6 is typically equal to square root of 3 over 2. So we already know one of the answers is going to be pi over 6 because that's in quadrant 1 and it's all positive. But we have to figure out the other place along this unit circle where the value would also be square root 3 over 2. So which other quadrant is cosine positive? Quadrant 4, which means this angle right here, my reference angle, is pi over 6. Is that angle?
11 pi over 6.
Ooh, how did you know 11 pi over 6?
It's just one less from 2 pi.
Yeah, remember this is 2 pi, a full circle, which is the same as 12 pi over 6. And if we're doing one less than 12 pi, it's 11 pi. So our two solutions for this side of the equation are pi over 6 and 11 pi over 6. So there are, in total, 4 solutions to part B. We had to factor it. We created 2 factors, and each of those factors are a level 1 problem. Yeah. Questions about these two before we flip it over? Because let's go ahead and try this one. So at this point, there are a few options for how we can do this problem. I'll go ahead and do the one that's on the notes that I printed out online, but I know 1000% there's another way to do this one, so if you can also see that one, that's cool. Here's what I see. I see that I have a squared term, which means I'm going to want to factor this. So to factor something, it has to be set equal to 0. So minus 1 on both sides. Now there's a chance this step doesn't always work, but it does in this problem, which is why I wanted to show you. Does anyone notice what kind of quadratic, trigonomic quadratic we have here? Don't think Pythagorean identities. Let me write it in a different way. Let's say it didn't say sine of x, it just said x. Does anyone notice what that looks like?
mx plus b.
Oh, sorry. That was supposed to be squared.
Oh, never mind.
I see that it's a subtracting of two things, and aren't they all perfect squares? So this is the difference of two squares with trig in it. Incredible, which means that this automatically factors to 2 sine of x minus 1 and 2 sine of x plus 1. And if you're like, what are you talking about? That's because the difference of two squares, if I just made it an x, this would be like 2x squared minus 1 squared. And the pattern says it should be the first thing minus the second, first thing plus the second. But instead of x, I have sine of x. That's the difference of two squares. So for later, when you're like, what did we do? We did the difference of two squares. Write that down so you know. So you're not like, what? Now that it is split into two factors, we take each factor and we solve it individually, which means we're going to solve 2 sine of x minus 1 equal to 0 and 2 sine of x plus 1 equal to 0. So far we have just factored. The factoring method we used was difference of two squares. Then we separate them into two problems, just like we did after we took the GCF on the other side. If we look at just the blue equation now, I can't do anything until it says sine of x equals. So what would I do first? Plus 1. But yeah. And then divide by 2. Ah, that should be something we recognize. Where does sine of x equal to 1/2? What angle measurement? Yeah, so we know just by looking at our chart and or remembering, sine of pi over 6 is equal to 1/2. Huh? Which means that we have two angles. We have this angle, which is pi over 6. Check done. And what other quadrant will we have an angle in? Yeah, sine is also positive in the second quadrant. So this reference angle would be pi over 6. But I don't want that reference angle. I want the obtuse angle. Yeah, 1 less than 6. So for the blue equation, the two answers that I have, the two solutions are pi over 6 and 5 pi over 6. After lunch, we will do the green side. And now that it's after lunch, we'll go ahead and do the green side, which again, the steps are going to be eerily similar, but this time we're going to subtract 1 to both sides, then divide by 2. And now we need to know where sine of x is equal to negative 1/2. But if we use the same idea that normally sine of pi over 6 is equal to a positive 1/2, that just means we're looking for the quadrants with that angle where sine is not positive. So which two quadrants is sine not positive in? 3 and 4. So we want this reference angle and this reference angle to be pi over 6, which means the obtuse and very, very obtuse angles, what would this one be?
I can't write.
It would be 1 more than 180 degrees. So 6 over 6 is 180, so this would be 7 pi over 6. And what would this one be? 11 pi over 6. So that means the other two solutions here are 7 pi over 6 and 11 pi over 6. So all of the pi over 6's, basically. Okay, comments, questions, concerns. So let's review what we did since we had a whole lunch break in between this problem. We factored the very beginning with difference of two squares. We use quadratics with trigonometry. Then we had the two factors that we solved individually to find all four x values where this is true. This next problem is going to introduce to you something that you have not seen before, but will be used in calculus a lot. It's called u substitution. It's only called u substitution because you use the variable u. Let me explain. Do you notice that this is a quadratic? And that if you were to let u represent cosine of x, anywhere there was a cosine of x before, I'm just going to replace with u to make it a little bit easier to see. Which means this would be 2u squared plus u minus 1 equal to 0. Now that actually straight up looks like a quadratic, does it not? And the way that we've been factoring quadratics is with the guess and check method. If you were never a guess and checker, this is the X puzzle, X box, however you learn to factor. But we're going to guess and check. How do I set this up? What goes in the first parentheses?
2u minus 1.
Oh, we'll just do the setup. So 2u, and then in the second parentheses is, okay. To do guess and check method, you want to figure out the factors of this number, which is 1 and 1. So obviously it has to be 1 and 1. One of those will be positive, one of those will be negative. Which one is positive, which one's negative?
And you're multiplying to get to the 2u?
Correct. You would want to be able to multiply this and this and then combine them to make 1. The one on the right being negative, one on the left being positive, bless you, means that this would be negative 2 and positive 1. Does that give me what we want?
Oh, you're multiplying those two.
Which is negative 2u and positive 1u. Does that make what we want? Yeah, we actually need to do the opposite way. So let me erase this. Guess and check. Okay. Great. But I was not actually doing a problem with u's in it. So I'm going to unsubstitute it. Meaning I'm going to put it back. This is actually 2 cosine of x minus 1 times cosine of x plus 1. This is called u substitution. I'm going to call it u sub. It's only called u substitution because you use the letter u. U is not a well-used variable in calculus, so it's a safe one to use in this situation, to just sub it in real quick, do some algebra with a simpler looking function, and then put it back afterwards.
Can you use another letter?
Technically, yeah, but you will see use substitution. That's like that's what you use. Don't use that one because it's function. It would be weird. Okay. At this point, though, we have it factored, which means we can separate it into 2 itty-bitty problems. 2 cosine of x minus 1 equal to 0, and cosine of x plus 1 equal to 0. What do I do with the blue equation? Add 1 to both sides. And then divided by 2. Okay. Do we recognize the number 1/2? Great. That's somewhere on our table. What is it a normal value for? Pi over 3. So normally, we know that pi over 3 would be 1/2 for cosine. In what other quadrant will that also be the case? 4. Because cosine is also positive in quadrant 4. But that means that this angle is pi over 3, the reference angle. What's the positive angle? 5 pi over 3. How did we know that? We know that because a full 360 degrees would be 6 pi over 3. That's 2 pi. And this is just one less than it, so 5 pi over 3. So for the first part of this problem, the two solutions are pi over 3 and 5 pi over 3. Now for the second part of this problem, we still need to solve it for cosine of x to be isolated. So we would just subtract 1 to both sides. Does -1 look familiar? Not from the table, but where does it look familiar from? Remember, if you're stuck on this, look at the very top of the formula chart. It's just one place.
Pi.
It's just here, which is pi. Yeah, again, you're looking at the top of the formula chart for this. I'll show you. Okay. Now, this next example is going to have a u sub in it as well. So before we show it, because I'm going to have you guys kind of tell me what to write down, what about u substitution is like still fuzzy? Because it's new, so it's going to be fuzzy. Do we see what I substituted out?
Yes.
And then it makes it a cube quadratic that we've been factoring since Algebra 1. And then we sub it back in. Okay, let's try it. So I need to do a u substitution. I know I need a u substitute because these do not have a GCF, and there's 3 terms. And the way we factor 3 terms is with factoring, so you doing a u sub is the only way to do this. What do I let u be equal to? Sine of x. Because this time, in the spot of where is normally the single variable, I have the whole function sine of x. Which means, how would I rewrite this question? Uh-huh. Uh-huh. Fabulous. So how does that factor? How do I set up the factor, I guess? Okay. Just regular u. It's always the first coefficient and the variable, and then just the variable. Okay.
And then that one's going to multiply with the 1.
Well, we just look at the factors of the c value in guess and check. So the only things that multiply to 1 are 1 times 1. But what signs do I use? Both positive, because we needed to add up to 3. After I do the factoring with the u's, what do?
You plug in the sin x.
Yeah, you undo the substitution, so you sub it back. So again, these steps right here are called the u sub steps. Once we have it factored, whatever it takes to get it factored, whether that's GCF, difference of 2 squares, or u sub factoring, we can set each of them equal to 0 and solve. Can I leave you with your team to work on this one and see if you can get it? All right, you got this one. I got you here. We got through the factoring. We got it set up to the 2 equations. Let's see if we got the finish.
Let's start with this second.
Okay, so since you had a moment to think, let's see what we would have done. I think pretty much everybody got to the point where we were at sine of x equal to -1/2. Did we all get there? So what I recognize is that typically we would have sine of pi over 6 equal to +1/2. That's about as close as I'm going to get in quadrant 1. But since it's negative, that just means that it's going to be in the quadrants where sine is negative. Which 2 quadrants is sine negative? 3 and 4. So my angles are going to be here, with these reference angles being pi over 6. So if that's the case, what is this full angle right here? 1 more than 6 pi over 6, which is 7. And what is this full loop going to be? 11 pi over 6, which is 1 less than a full 2 pi. So my 2 answers here are x equal to 7 pi over 6 and 11 pi over 6. Now, a couple questions that I'm getting a lot on this is trying to remember which quadrants it's positive in. Remember that goes back to the all-star trig class. Or look at your formula chart. Again, those unit circles at the top have pluses and minuses for the quadrants where that sign or that trig function is positive or negative. So you can look there. But of course, we're not finished. We still have the second factor to solve, but I think I saw everybody had this one for the most part. This would be sine of x equal to -1, and -1 I recognize as a part of my unit circle. It would be this down here, which is what x value? Actual question. 3 pi over 2. Okay. Cool. We're getting it. Now always remember, you can verify on your formula chart for all of the places where sine is equal to -1/2 and sine is equal to -1. They're all on that list for cosine, that column for cosine. One last question here. Oh, I lost the question. There it is. 3 tangent squared of x minus 1 equal to 0. Now this looks like the problem C at the top of our paper, but is this a perfect difference of two squares? No, because 3 is not a perfect square. So we're going to have to do something different. And what I'm doing on this problem, you very well could have done on part C if you didn't notice the difference of two squares. What we're going to do is we're going to isolate the single term that is squared, meaning I'm going to add 1 to both sides, and I'm going to divide by 3. Now, if this were a regular x squared instead of tangent squared, how do you get rid of a square? Great, so we're going to square root both sides, but when we square root both sides, because you chose to square root it, what do you have to add? The plus or minus, don't forget this. When you choose to square root something, you are leaving out the option of the negative version unless you put plus or minus there. It is in the formula thing we did last time, but we're not using that. So, no. It's not the sum of tangents. There's not two angles here. Here's what I see. What are those called? Radical rules, when it comes to algebra 2 style rules, means that I can split that radical to the top and the bottom. But then I have a radical in the bottom. Do I like having radicals in the denominator? No. So how would I rewrite this?
I know the denominator is 3.
We know the denominator's 3. Okay. What's the numerator? Square root of 3. Oh, does that look familiar to us? Square root 3 over 3 with tangent? So normally on my formula chart, I know that the tangent of what is square root of 3 over 3? Pi over 6. But I want all of the square root 3's over 3's because I want the positives and I want the negatives. So let's do with positives first. So in which quadrant is tangent positive? First and the third. So we know this first one is pi over 6. We don't have to do anything special in the first quadrant. And we know that this reference angle is pi over 6. So what's the obtuse angle there? 7 pi over 6. Cool. But then I also need the negative versions because it says plus or minus. So what two quadrants is tangent negative in? 2 and 4. So these reference angles are also going to be pi's over 6's. So what's the angle in quadrant 2? 5 pi over 6. And what's the angle in quadrant 4? So all of the angles that are equal here are pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. That's the weirdest looking pi I've ever wrote. Okay. So if you do the problem like this, you just have to make sure you don't forget that plus or minus, or else you're only giving me half of the answers. Now again, I could have done problem letter C the exact same way if you did not notice that it was difference of two squares, because it's set up the same way. Now part F, you could not do a difference of 2 squares, so we had to do it this way. And if this is easier for you than doing difference of 2 squares, then do them all like this when there's only one term and it's squared. Solving by square roots is what it's called. So that is solving trig functions. We're doing a lot here. We're mixing algebra with trig at this point, quadratics with trig, and the trig values. We're doing so many things. Amazing. Are there any last minute questions before we're done with notes?